right, oops, something got superimposed on it. All right, so from another presentation, the title of this presentation is Absorption Line Spectroscopy in Practice. So I gathered a few examples of non-standard situations that I wanted to show you that had to do with absorption line spectroscopy in the X-rays. And from a previous presentation, something is embedded in this file that I used as a template that now says astrophysics, nuisance, and opportunity, which is sort of appropriate, actually. So I've been doing some work with a whole group of students, and I've listed all of them over here. So I would like to acknowledge their contributions to some of the stuff I wanted to show. And the first thing I wanted to show was a situation in which we had a funny absorption line profile. And this has to do with the study of the interstellar medium that I initiated with John Stanton, my student. So we were interested in trying to pursue absorption spectroscopy of the interstellar medium. There's lots of questions open on the interstellar medium. And one of those, for instance, is what is the dominant, is there a dominant form in which carbon exists in the interstellar medium? Is it in, when it is in solid particles, is it in graphite, in graphene, is it in polycyclic molecules, etc.? And X-ray spectroscopy is a perfect tool for addressing this sort of question because, as you probably know, the energy levels in an ion or an atom respond to effects of binding and ionization to the tune of about shifts in a few percent in transition energies in response to a single step in ionization. And that kind of thing we can nowadays actually resolve with X-ray spectrometers. So you see small shifts that are the response to chemical effects and ionization effects in the energies of edges and lines. And the other thing, of course, is that all the ionization stages have their K-shell spectra close together for the low Z elements. And so a single X-ray spectrum can, in principle, reveal the physical state of an element in all its possible ionization and molecular states. And so one of the things we wanted to look at was carbon, because there is a lot of carbon, and also because nobody had done it before, as far as we know. And as I'll show you in a moment, there's a formidable obstacle to doing that, and that has to do with the instrumentation. So as an example here, I showed the K-shell energy range for the carbon atom, so around 280, 320 electron volts, and you can see the absorption due to neutral carbon over here. This is carbon in a layer of graphenes, 2 layers stacked, 3 layers stacked, 4 layers stacked, and you can see how the photoabsorption cross-section increases as you add more layers, and you can see how the structure of the absorption also changes as you do this. So this is the sort of thing we were going to try to see. Now, of course, the problem is that, as you probably know, the one spectrometer that will allow you to do this is the LETG, because it has sensitivity that runs out past the carbon K edge, and it has sensitivity and resolution at that range. But as you are probably aware, there's a beam filter in the LETG that shields it from, that shields the detector from UV radiation and charged particles, and it has plastic in it. Plastic means carbon. And so if you look at the spectrum of Markarian 421 in the carbon K range, this is the carbon K absorption edge range for Markarian 421. This is a paper by Hasselblad and his colleagues in 2010. And most of the absorption you see over here can be attributed to absorption in the plastic filter in the instrument. And so here, this is the long wavelength side. This is where the photoabsorption has set in. Here's a 1s2p transition in neutral carbon. There's also evidence for absorption that is not associated with the plastic. So there's some interstellar effects. This is probably absorption over here that's due to singly ionized carbon in the ISM and possibly doubly ionized carbon. So the transmission of this filter was modeled. Hasselblad and his colleagues used an extensive calculation for neutral carbon, atomic carbon, to model this transmission curve and fit it, and said then that must be the plastic because the interstellar column density towards Markarian 421 is small enough that we would not expect significant absorption by interstellar carbon. So John Stanton went ahead, looked through the database, found a few objects that actually do have a significant column density in excess of the one that sits in front of Markarian 421, and they're also bright sources, and the brightest one he found was 1ES 1553 plus 113 of intergalactic absorption fame. You probably remember the papers by Fabrizio Nicastro on that subject. And he looked around the carbon K edge, and he convinced himself that there is, in fact, something to be detected over here. So he gave me this version of a plot we recently made. It shows in black the data points around the carbon K edge. So this is around the carbon K edge 285 eV, 290 eV over here. And superimposed in blue is the response that corresponds to this red line over here. It is basically just the absorption in the plastic filter as it showed in Markarian 421. So John took very precise care to take the spectrum of Markarian 421, remove all the effects of the higher orders, remove the effects of the slope of the power law, et cetera, et cetera. And so, and the tiny residual effect of the absorption due to the interstellar hydrogen and helium and a little bit of carbon in the ISM in front of Markarian 421. And he was left with a function that basically represents just simply the response of the instrument. So that's the blue curve over here. And as you can see, in it is present this carbon 1s2p transition or 1s2 pi star in carbon bound to carbon. There is this little dip over here that was identified as absorption in singly ionized carbon. And then this is where the carbon, there's another neutral carbon absorption feature over here. So there's this funny shoulder over here that is not seen in any other source that we've looked at. There's a few other sources that have some absorption along the line of sight, and they never show this. They always conform to this shape of the absorption edge. And this is a pretty significant deviation. So we called this the red shoulder, and we were wondering what this meant. Incidentally, so Leah Corrales will probably tomorrow discuss absorption spectroscopy of the ISM in more detail. We were actually looking for some stuff that was occurring over here. And so we were not really focused on looking at interesting features over here, but this is what we found over here. We found that there was probably not enough signal to noise, even in a very bright, long exposure source, to do something useful with for carbon. So we looked at this feature over here and we said, like, all right, this actually looks fairly wide, and it looks wider than you would get for a typical absorption resonance. If you remember, the polarizability of a molecule or an atom has an imaginary and a real part. The imaginary part is the one that actually gives rise to absorption of radiation. That typically has a Lorentzian shape that's pretty narrow. That's indicated over here. And then there's also the real part of the index, the phase shift, that usually has a shape near a resonance that looks like this. So this is a plot I took from your textbook on classical electrodynamics. And if you simply calculate the response of a harmonic oscillator to an incident harmonic field, this is what you get. So this white piece over here is the real part of the index of refraction. And that is the part that is responsible not for absorption of photons, but scattering of photons. And so we were thinking of the following possibility. Scattering of radiation in the ISM, of course, contributes to extinction. And if the scattering angles for radiation are large enough, radiation will basically be removed from the direct beam so far away that you don't really take into account that it exists. It's spread all over your images, or maybe even outside the borders of your image. And for all practical purposes, the scattered radiation looks like just absorption. The transmission of the ISM will exhibit a dip that is the result of radiation having been scattered out of the line of sight. So scattering angles for the carbon K edge that we were interested in, if we think of little particles of radius A that have a radius of 0.1 microns, roughly, which is a characteristic size of interstellar dust particles, the radiation wavelength is about 44 angstroms. So scattering angles for 44 angstroms off of particles of that size are of order degrees, meaning that once a photon scatters off of a dust particle, it will just be removed altogether from the consideration. So that several degrees, of course, is much larger than the Chandra angular resolution, and these spectral images will just simply show a dip in the region where the light has been scattered out of the image. It looks like absorption. And so we came to the following interpretation. There is good evidence, there's calculations for the real and the imaginary parts of the response of graphite particles, which is one candidate possible particle in which carbon might be sequestered in the ISM. There's a nice paper by Bruce Drain from 2016 with characteristic thoroughness. The paper is actually called Graphite Revisited, so that says it all. And here's a picture of the polarizability of graphite particles in the carbon K range over here, 280 to 340 electron volts. This is the imaginary part that's responsible for absorption. So if you look at the red curve, for instance, here's the narrow resonance over here. And here's the real part of that response. And you can see that there's still, even for a real atom, there's enough of this white wing-like structure left that we saw for the response of a simple harmonic oscillator. There's a blue and a red curve here for both parts. So let's look at the real part for now for the scattering part. Graphite is actually a pretty seriously anisotropic material. It consists of a series of graphene planes that have been loosely bound together like this. And so it does matter whether radiation, if it's polarized, if it comes in with the electric vector perpendicular to those planes or parallel to those planes. And these are the two different responses for those two cases. The red one is the one that has the electric vector perpendicular to the graphene planes. And that's perpendicular to this symmetry axis for the crystal C. So that's why this is called E parallel to C. So we use these scattering cross sections to calculate these polarizabilities, or dielectric tensors, or whatever you want to call them, real part of the index of refraction. And we calculated the scattering cross section for particles of order 0.1 to 0.2 microns. And for a column density that has an amount of carbon in it that is appropriate to the neutral hydrogen column density in front of 1ES 1553. And over here, I've superimposed two pictures on each other. One of them in faint blue is the one that I showed you earlier. That's the pure response of the instrument. The data points are shown over here. And as you include this scattering effect, you can see that this edge starts to round away. And so this here was calculated by John using just simply randomly oriented particles and no particular polarization for the incident radiation. But of course, we're looking at a blazar, and so it is possible the radiation was in fact polarized, or is polarized to some extent. And it's also possible that small particles are aligned in the galactic magnetic field, in which case this effect would become more pronounced. That would actually correspond a little closer to these data points over here. So it's an interesting suggestion, and this might be a way of actually finding out about alignment of the carbon particles in the ISM in a way that's completely independent of any optical studies. So as a byproduct, you see that this real part of the index of refraction also takes care of the spectrum over here, which is an interesting fact. So that's what we did on an unusual absorption line profile.
Great, yep. It wasn't bad. I've got a couple questions, yeah.
Good, not bad. I guess that's good.
Yeah.
Yeah, Mike. Tim, can you mute your microphone? I think you're unmuted. Or Randall or Adam, could you mute Tim's microphone? Sorry, go ahead, Frits.
Oh, it's Tim. All right. Okay, so so that was an unusual absorption line profile, which turns out not to be an absorption line profile. And I think we've been able to interpret it, and we've actually drawn conclusions about the ISM that we thought were pretty exciting. The other thing I wanted to show you is a practical case that had to do with the analysis of the spectrum of a nova that went off in 2013, Nova Delphini 2013. And one reason we were interested in it initially was, as you can see, the spectrum over here, which I pulled out of TG-CAT, the praises of which need to be sung at every possible occasion. Here's the carbon K edge, and so you can see it's very strong, and so we were interested in also at some point looking at the interstellar medium along the line of sight and the circumstellar medium, because there's the suggestion that novae actually produce in their later stages big clouds of dust, and so perhaps we will actually be able to see dust clouds forming, carbon dust clouds forming along the line of sight by looking at changes in the X-ray absorption spectrum. There are changes, but we're not at the point where we can quantitatively interpret those. So I'll show you what we ran into first. So this is work I'm doing with John Miller. To first order, this spectrum was taken in November 2013 with the LETG. So from 20 to 50 angstroms I've shown over here. There's no radiation shortward of 20 angstroms. This spectrum to first order looks very much like the spectrum you would expect from a hot white dwarf photosphere with an effective temperature of about 700,000 Kelvin, which is what you would expect in the aftermath of a nova. Thermonuclear fusion has heated the surface to of order 1,000,000 degrees, and it's slowly cooling away. And we're just seeing X-ray emission from the stellar photosphere. And probably most of this structure you see over here are absorption lines, stellar photospheric absorption lines in the atmosphere of the white dwarf star. And you can see that this is an extraordinary spectrum. I've binned it up. You can see it's 10,000 counts per bin over here, right? This is a beautiful set of data to work with. So the spectrum is actually variable. If I overlay two spectra taken in November and in December of 2013, so roughly 4 months after the nova eruption, you can see that the spectrum changes from November to December. In December, I've indicated in faint, and the brighter one is the November spectrum. There are small changes in the amplitude of the spectrum over here, but you can see that there's something pretty drastically changing over here. And then if you look more closely over here, this thing over here was a pure absorption line in November, and in December it starts to develop, as you can see over here, it starts to develop a central reversal in it, an emission reversal it looks like. So it looks like emission lines are growing, probably to do with stuff flowing off the photosphere that has low densities, and we're starting to see emission from that material that sits well above the stellar photosphere. So now this is a really complex spectrum, and John played around with published models for white dwarf photospheres, got a rough fit to show the right, roughly the right amount of light in this bump over here and the right amount of light at longer wavelengths. This is still with the instrument response in it, of course, so that's why there's this big gash due to carbon. But then none of these features actually fit in detail, and so we decided we had to get to work, so we put on plastic gloves and we're starting to pull the spectrum apart. And the first thing we noticed that there's definite evidence for very strong circumstellar absorption. So you can identify the carbon-6, the hydrogen-like carbon Lyman spectrum easily. You can also see carbon-5 absorption. There's also nitrogen 6 and 7 absorption. So those are the ones we started with. And the reason that we know for sure that these are not in the stellar photosphere is that they're all offset by a huge Doppler blue shift. So we're now doing Doppler spectroscopy, starting with lines for which we actually know what the wavelength should be, and the simple hydrogen and helium-like ions of carbon and nitrogen, oxygen, possibly neon, are the simplest way to start, of course. So that's what we started with. And then we ran into a funny problem, as we'll discuss in a moment. So here's a little piece of the spectrum, and this source is so bright you can actually look at the third order. So the reason I did not show you the spectrum longward of 50 angstroms is it goes through a bit of a depression over here, and then there's a huge bump of radiation that comes back at longer wavelengths. That's not the source itself mostly. In fact, it is all third order radiation. So you can actually see the first order spectrum. You can see the third order spectrum at 3 times the original wavelength. So this is a piece of the spectrum around the carbon-6 Lyman alpha transitions. So those are at 33.741 and 33.735 angstroms. So multiply by 3. That's why this is between 99.5 and 102 angstroms. And over here is, in fact, the rest wavelength of the carbon-6 Lyman alpha transitions. And there's a little bit of a dip at V = 0. So that might actually be the absorption in the star itself that has maybe a very small radial velocity. That might be the absorption in the stellar photosphere. And then over here is this huge thing over here that we have identified as carbon-6 Lyman alpha in an outflowing shell of material. You can actually see in the optical that there's material outflowing not long after the eruption. So we're not surprised we see outflowing material over here. So this big thing over here has an offset of about 1,300 kilometers a second blue shift. So that might be material in a wind that's actually moving towards us. And so this is the resolution of the spectrometer in third order. And this is about 300 kilometers a second over there. So this is a huge shell of material that's moving towards us. So the reason we actually believe that this is the carbon-6 Lyman alpha, and we're not looking at this thing over here, is the following. When you plot this on a velocity scale and you look at n = 1 to 2, n = 1 to 3, 1 = 1 to 4, 5, 6, and at that third order profile of n = 1 to 3 on a velocity scale, right? Then you see that they line up over here. There's absorption at 1,300 kilometers a second that has a counterpart in at least n = 1 to 4 and n = 1 to 5 and 6. As you can see, n = 1 to 3, the Lyman beta, there's something else superimposed on this. We don't know what to do with this. So this thing is totally unrelated, has nothing to do with carbon. And so this Lyman beta absorption spectrum we cannot use for this analysis. You can see that there's problems with trying to establish where the true continuum level should be for this object. So the one thing you might try is to actually do a curve of growth analysis, for instance, get the equivalent width of all these lines and then plot them on a curve of growth to see if there's a single absorbing column density that will represent all the measurements. And we've basically failed at that because we don't really know where to put the continuum level. And even if you make extreme assumptions, take the largest and the smallest possible cases for the equivalent width that you can find and plot them on the graph and then see if there's a solution. It ends up being very confusing and contradictory. So I think at this point, we're going to have to decide that we'll just simply go with the absorption line we understand best. This has a few hundred kilometers a second, 300 kilometers a second width. It appears not to be saturated at the center. So under the assumption that all of the absorption is optically thin, we can use this absorption line to derive the column density of material that's outflowing, and then we can estimate the mass of the gas that's outflowing, and we can estimate the kinetic energy of the material that's being expelled and compare that to the nova outburst. And we can also use the fact that we see all this stuff happening at minus 1,300 kilometers a second to start looking at the rest of the spectrum and cross off lines that are clearly associated with this shell of ionized material that's flying away, so that we can actually focus, if we would like to, in the next step on what are truly photospheric absorption lines. And as you saw in the example of the carbon, right, this thing over here is the photospheric absorption. This has nothing to do with the star anymore. And so just simply to reduce the spectrum to something that's interpretable in simple terms, we're going to have to go through this.
Frits,
And
you're
so,
at 20 minutes. So you have
yeah, this is almost the last slide I had. We did the same thing for nitrogen 6, just as an example, same velocity offset, so that reinforces our confidence that what we're doing is more or less correct. And this is a summary of the argument I gave you earlier. Lyman alpha is possibly saturated, but Lyman beta is not usable, and the continuum levels at the other Lyman series members are too flippant to be able to actually make a curve of growth that is interpretable in simple terms. And so we're going to ignore and discard the higher series members and just use the Lyman alpha profile, and we'll use the m=3 profile, the third order profile. And then we'll get the mass and kinetic energy of the scale. So I put together 2 statements of general validity and possibly of educational value. Basic physics is fun, and it pops up everywhere. And John and I were both delighted that it turned out that our instincts regarding the shape of that absorption feature in the carbon absorption spectrum towards 1ES 1553 does in fact correspond to what we had read in textbooks, right? So it's fun to be able to use the things that you've learned and apply them to real data. And I think it's also important to, if you look at confusing data, to be prepared to ignore confusing evidence if you can identify a rational basis for doing so. Because to quote Claude's talk at one of the early spectroscopy talks after we had first gotten access to CCD type spectra, you looked at some very complex spectra from AGN and supernova remnants and says so. And I remember him grabbing his head to say, we're going to have to somehow figure out how to diagonalize this matrix. There is so much information in here. So part of the art of doing spectroscopic analysis is also to find a basis for crossing off stuff that just simply seems to be confusing and cannot possibly be a major part of the answer to the question you're trying to answer. In the last remaining minute, I had one encore. I've also been doing some work on Cygnus X3 with Ashwath Suryanarayanan, and Ashwath found that he could extract the third order spectrum from Cygnus X3, which is extraordinarily bright. So here's the third order spectrum, which has a resolution over here that is of course 3 times narrower than the first order spectrum. And in third order, you can actually see that you can resolve the helium-like emission lines from iron 25. And so here's the resonance line, and in this clump over here must be the intercombination and forbidden lines, and there's probably also a whole series of satellites from the lithium and beryllium-like ions present at the same time, which is not unexpected in a source that's dominated by photoionization. Ashwath found evidence for what appears to be on the resonance line, the W line, an absorption component to it, so we can actually see that there is in fact a p-Cygni type profile in helium-like iron along the line of sight. There you go. And as Tim pointed out earlier, in pure recombination situations, this W line is expected to be fainter than the X, Y, and Z lines. And in this case, that does not appear to be clearly the case. And that would be evidence for another process contributing to the brightness of the W line. And then the natural explanation for that would be photoexcitation, scattering of continuum photons by the resonance line into our line of sight. And so I would like to express my gratitude to everybody who has listened and to all the students who worked with me so far over the summer under interesting circumstances. And I have the best wishes for everyone, and I'll take your questions.
All right, thank you very much. And I also want to put in a plug for TGCat. That is a very valuable resource that you can get a lot of.
And you can do it while you're just having a cup of coffee, right? You're reading the paper, you think, oh, wait a minute, and ta-da, 3 minutes later, you're in business.
Yeah, absolutely. And David Hunemuller, I think, is on. So if anybody has any questions about TGCat, he's probably the one to ask. Okay, so we have one question on the Q&A from Ephraim Brown. This is regarding Nova Delphini's December 6th spectrum. And the question is, what physical mechanism could underlie an emission that takes place at the same wavelength as an absorption? So where are these, where is the emission coming from versus the absorption at that same wavelength?
In the nova. So if there's a shell of material that's moving away, it currently has a radius that's many, many, many times the size of the original star. So if there's a shell of gas that's getting thinner and thinner, the density is dropping and dropping at some point, and the absorption cross-section in the ion you're talking about is still really large, then you'll start seeing photons whose last interaction was in a shell of material that's far away from the stellar photosphere. So you'll see the absorption that happens deeper in the stellar photosphere, and if gas sits above that region and is at very much lower densities, you can actually see the photons that were produced in emission from that layer escape. That's the classical explanation for reversals in stellar spectra.
Okay, great. And we actually have a bunch more questions. Probably have time for just a couple.
Okay.
So Junjie Mao asks, what if part of the carbon is amorphous? Would that help to bring the model further down to meet the data?
If the carbon is amorphous, so well, okay. So the thing that we identified as possibly due to scattering, it relies on the presence of carbon-carbon bonds, and the carbon-carbon bonds would be present to some extent probably in amorphous carbon. Depends on what you call amorphous, right? Truly amorphous would just be a bunch of atoms that are stuck together with very little chemical bonding. But if there's any bonding going on, if most carbon atoms are bound to at least one or two other carbon atoms, you should probably get something in there. If it would make it better, then if the carbon is truly amorphous, of course, the effect is no longer dependent on the polarization. And so you could assume that all the carbon effect produces the scattering instead of only a fraction that is aligned and responds to polarized radiation. So it might relieve the bounds on the amount of carbon that's available for producing this effect. Yes.
Okay, great. And then one more question from Chris Stone. I should point out, Frits, that there's an additional question from Daniel Rogantini, which is on Slack, so I'll let you answer it there.
Okay.
But the question from Chris Stone is, for Cygnus X3, how many separate lines do you see in iron 25?
Well, at least a couple. Hold on, let me. You cannot see my screen anymore. All right.
Yeah.
Hold on a sec. Share screen. You have to click the little share box. I always forget. Okay.
There it is.
There it is. And all right. So it is confusing because the W line stands out for sure, right? Z is supposed to be somewhere in here, and X and Y are supposed to be sort of not where they're so So we actually think that the satellite emission is significant in this region, and the spectrum is too faint to tell definitely the individual lines. Those individual satellites are each separately present. So beta is expected to be really bright in the lithium-like ion. Maybe that's in fact what's over here, but that's as far as we can go.